Okay, so the goal this morning is to prove two things about the Coulomb gas. One which is called local laws, and the other one which is some almost additivity of the free energy. Okay, so these the meaning of these two words will come, and these two things are going to be very closely related. So before I start stating stuff, I want to do something which is convenient, which is not essential, but it's convenient for the clarity of the expressions, which is I want to rescale the system. Okay, so I want to rescale in the following way. I had my system, my Coulomb gas is living in a region. So you remember sigma, for instance, the support of the equilibrium measure is of finite size, and here we have n points. And the typical distance between points would be n minus 1 over d. So I want to multiply everything by n to the 1 over d. And then find myself with a system which is very large, 1 over d. But now the points are kind of well separated. Okay, so to do that, we're going to put primes to everything for a minute. So the points are going to be xi prime is n 1 over d times xi. The whole configuration is going to be also zoomed. And the equilibrium measure, or the background measure, mu, is going to be changed into mu prime, which is mu of n minus 1 over dx. Okay, so when x here is, when x here is of size n to the 1 over d, then this becomes of size 1. Okay, and so when you do that, the mass of mu, so mu was a probability density, but this one is not going to be a probability density. This one is going to have integral equals to n. Okay, so we have a measure of mass n, but that's okay. And then I'm going to define f of x n mu. So it's almost the same as my f before, but it doesn't have the n subscript. So that's going to be the same energy, g of x minus y, except now there's no n in here. And the rescaling formula is that f of xn prime mu prime is equal to n to the minus s over d times fn of xn mu plus this n log n term that we had floating around all the time if s is 0. Okay, so obtaining this formula is not difficult. You just plug in. And you see that whenever you have g of x minus y and you rescale, you're going to get a factor n s over d that comes out if s is not 0. So when you're multiplying all the lengths by n to the minus 1 over d, to the 1 over d, you get a factor n minus s over d. Except that if it's the logarithmic case, when you rescale, you get an additive term, right? Because the log is additive with respect to product. And so this explains somehow why we were always finding expressions of this form. And I was telling you, in fact, what you should think of as the energy is this whole package, the whole sum of the two things in the logarithmic case. Okay, so with that, when we had the Gibbs measure, we reduced it to some, so P was equal to that. That was equal to E to the minus beta n minus S over D Fn, right, divided by Kn beta of mu. And now maybe you see why it's convenient to have this factor n minus S over D in front, because it's going to exactly match the rescaling formula. So now in rescale terms, we can also say that this is equal to e to the minus beta and f without the n now anymore. And there's going to be a different normalization factor. Here it's convenient to divide by n to the n, which is the mass of mu prime, in fact. Because mu prime is no longer a probability, so we can write it like that. Integral of mu to the n. And k beta of mu. And now we're going to define k beta. It has okay, so this is now our new partition function in scaled coordinates, and now you see it's nice because there's no longer these weird factors floating. Okay, so the question is to first question is to study the log of this quantity. So if you remember yesterday or the day before, we obtained some a priori estimates on the free energy when it was defined like this. And the estimates were in beta, chi of beta times n. Now, if you rescale things, you can check it's going to be, because of the way things have been scaled, it's going to be the same. Beta, chi of beta times n. Right, it was our a priori estimate. Chi of beta is a factor that's there for small beta regimes. You get a sort of extra term, like there's a bit more free energy in that case. And there's a constant here, and the constant is independent of beta and n. Depends only on mu, the L infinity norm of mu, the dimension, and that's it. And okay, so one way to understand this this inequality is that now we have a system, and we think of it as living in a volume n. Okay, so this has volume n, and n is also the number of points, right? So this is the right order, and so now it says that when you're in the whole region, the free energy, which is this log k, is proportional to the volume, or it's controlled by the volume. Okay, so one of the questions we're going to ask is, when I restrict myself somehow to subregions, do I keep a free energy that's proportional to the volume? But I have to define what I mean by the free energy in a subregion. Okay. So in order to understand this, we're going to define two different variants of the energy. So remember, now we have e to the minus beta fn, f of x and mu. I'm going to now make a simplification for the presentation, which is the electric formulation of f, which is written here, is something like this. I can write that this is equal to some term like that minus renormalization terms, right? So the terms that would contain some of G of Ri and extra terms. So if you remember from 2 days ago, there was an equality case. If my balls are disjoint, I have an exact equality. And what is H here? Now it's in rescaled coordinates. So when you're in rescaled coordinates, you don't need to put an n here anymore. You just have minus mu, because this thing is mass n, and this is mass n, so you have your neutral system. And here you have your Ri. Okay? And so from now on, I'm just going to not write down the renormalization terms. Okay? I'm going to do as if I'm going to call this grad hn squared, and you will understand that this means in a renormalized way, because it's not essential for the arguments, right? So in the back of our mind, we know we have to do that, but we won't write it. Okay, so now this becomes a fairly simple expression. And as I mentioned on the first day, the nice point of this electric reformulation is that it transforms a double integral that contains all the pair interactions into a single integral in terms of the potential. And this integral is something that's extensive in space. Right? So we can start to restrict the energy to subregions of the space. Maybe I have to delete that as well. Okay, so if I have f equals some constant times this, I can define, if I want, for given omega in Rd, I'm going to define this, for instance, f omega is going to be the same, but integrated over omega. Right, so I can just restrict. I can just restrict my integration to a subregion. And this will be understood as, okay, we're looking at how much energy is in that subregion. So it's not quite that you're taking the charges in that subregion and you're looking at their interaction. It's something different. Because this thing, if you want, is still non-local in terms of the points, right? The potential H is something non-local. It depends on all the configuration, and you're integrating it in a region, so it depends also on what's outside. Right? It's not like you're localizing completely, but you can always define that. And what we're going to show is that somehow it's a good approximation to think that it doesn't really depend on what's outside. That would be an ideal situation, and we're not very far from the ideal situation. Okay. So now we're going to introduce two approximate energy quantities. In a cube. Okay, so my omegas, I'm going to take them to be cubes. And the cube, we're going to call it Q. And it has, it has a size R in blown up scale. For now, R can be anything. Okay, so we have a cube of size R. We have points. And the first quantity is going to be expressed in terms of a function u, which solves the same thing that H solves. So minus Laplacian is CD blah, but with a Neumann boundary condition on the boundary of the cube. Okay, so it's not quite equal to H. It solves the same equation but has a different boundary condition. Okay, so if anyone has taken some PDE in their life, you should tell me whether this equation always has a solution or whether there is a restriction. It's a linear equation, Laplace's equation.
Right-hand side should have mean 0.
Yes, exactly. So when you integrate, right, you can integrate both sides of the equation and apply Green's formula. When you apply Green's formula, you find the integral of du d nu, and that is asked to be 0. So it better be that this right-hand side integrates to 0. Okay, so this is solvable if right-hand side integrates to 0. What is the right-hand side? It's the number of points in Q equals the integral of mu. Okay, so this is an integer. Call it little n. It's the number of points that are in the box is equal to the integral of mu in the box. So what does that mean? That means my box is exactly neutral. Okay, so the mass, the negative charge in the box is exactly equal to the positive charge in the box. Okay, so if things are neutral in that box, then we can solve, and then we define the energy, and I'm going to still call it F, and it's on purpose, in fact. So we're going to say that F of my configuration that has little n points with background mu, but in the cube. Right, so now there's a sort of third entry here. That thing is going to be defined as integral of grad v squared in the cube. And of course, this is to be understood with the renormalization, because otherwise this is infinite. So if it happens that your cube is infinite, right? So if the cube extends to be Rd, then essentially this is the same as H. This boundary condition is sort of true on the infinite space, and you recover F. So that's why it's a generalization of F, just a restriction to cubes, and it's a reason for keeping the same notation. Okay, so when we have a system like that, where you can solve Neumann stuff, we call this a screened system. For reasons that I will explain in a bit. So when you have solved all that. Okay, so this is a screen system. And now there is another quantity. We're going to do the same, solve the same equation. But this time with 0 condition on the boundary. It's called Dirichlet boundary condition. And now this one, from the point of view of PD, you can always solve. And we're going to find G relative to this cube as this the energy of that guy. Okay, so why are these two approximate energies? Well, the idea is that the true energy in the cube.
Just
yeah.
The screening system, the F is with the U solution to the Neumann problem?
Yes.
Okay.
Oh, sorry, this is a U. Thank you. Good point. This is a U. I hadn't introduced V. So this is U and this is V. And so the idea is that the true one, so the one that has the H is the one that's defined on the whole space. More or less, it's in sandwich between the two. More or less. Okay, so it's going to be interesting to look at these two quantities because the real one is somewhere in between. And the point is that this energy, this one, is going to be, I made the same mistake, V. This one is going to be super additive, and this one is going to be sub-additive. Okay, so this idea of, at least the way it's formulated here, of using sub and super additive quantities to sandwich the energy from above and below is actually inspired from work in homogenization by Armstrong and Smart. And if you came to Chen Lin's lecture yesterday, he gave a little bit of a glimpse of that in a different context. But. Okay. So why is this super additive, sub-additive? So the first thing is, when you want to minimize, let's say, I pose this problem, minimize now integral grad W squared over a certain cube, with Laplacian W equals something given. So this is a constrained minimization. I give myself a Laplacian, and I want to minimize the Dirichlet energy in the cube, and I don't say anything about the boundary. What is the solution? What is the best solution doing? So of course it's solving Laplacian equals blah, but it's going to pick a behavior on the boundary that's optimal. And the best behavior is to be constant on the boundary. Okay, so minimizer solves W equals constant on the boundary. How do you find that? So it's again calculus of variations. I've shown you the other day how to do variations for the equilibrium measure problem. So here what you can do, the only thing you can do, okay, you want to perturb W, the minimizer. You want to change it into something else, like W plus T phi. But you have this constraint that the Laplacian has to be given. So the only thing you can do is to take phi that's harmonic. That solves Laplacian equals 0, because then it will still be in the admissible class. Right? So Laplacian of W plus T phi will still be the given thing. And now you can say, well, this guy has a bigger energy than that guy if W is the minimizer. And this is for every t and for every phi harmonic. Okay? So now you expand in t, you do a Taylor expansion, you do some integrations by parts, blah, 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 and you're going to find, without too much effort, that W is constant on the boundary. And now this problem, as you see, is unchanged by addition of constants. So W is really only defined up to a constant. So we may as well assume that, or say that W is 0 on the boundary. Okay? So to come back to our problems here, this guy, the V, this one is the one that has the least possible energy given this right-hand side. Okay? So V has least possible energy In particular, you see this inequality is true, because this one must have less energy than that one, for instance. Okay, and that is going to yield superadditivity in a very simple way. So what do I mean by superadditivity? First, I mean that if I have a region, well, not necessarily, now it's no longer a cube, but it's like a rectangle, which is the union of two cubes. And if I form the G energy for the union, it's going to be bigger than the sum of the G energies for each part. Okay, so I have two cubes. I can talk about G of my union of two configurations in the cube, I mean the union of the two cubes, right? So what is that? That's the integral of grad V. Let's call it like that, Q1 union Q2 square. I'm going to drop these CDs in front. They bother me for nothing. So this is in Q1 union Q2, right? And that is certainly the integral, the sum of the integrals over Q1 and over Q2. Okay, but now when we're in Q1, this guy has the right Laplacian. It has a Laplacian equals to the sum of the charges that are here. So for that one, it's a competitor for the V of Q1. Okay, but V of Q1 always does better. It does better than everything. So this is bigger than grad V Q1. And this one in the same way is bigger than grad V Q2. Okay, and this is what I meant by superadditivity. Okay? Now the other guy, the U, the energy with the U, which is the F energy, the inequality is going to go in the opposite direction. And that is, so if you want, this is just by restriction, right? And for the other direction, it's going to be an L2 projection property. So there's a little lemma. Now it's a little more subtle, but not that hard either. It's going to be interesting to consider not only solutions to Laplacian equals a right-hand side, but to consider vector fields. We're going to consider vector fields. Yeah. So think of E like grad H, but not necessarily. And so we think of it at grad H, so then it solves minus divergence equals a certain right-hand side, something like that. And we're going to ask that U minus grad U, so it's my function, dotted the normal is 0 on the boundary. So you know that this actually is just the same as minus div grad u. So in other words, E and grad u have the same divergence, and their difference is normal to the boundary. Sorry, tangent to the boundary. Then, so the lemma says that the integral of grad u squared in the cube is less than the integral of E squared. So I'm going to give you the proof. It's an integration by parts, right? So we're going to write E squared. We're going to write it as E minus grad u, or as grad u, plus E minus grad u. So far, nothing. And now we expand. So this is a quadratic thing. We expand. So there's going to be grad u squared plus E minus grad u squared, which is nice. This is as a sign, plus integral of, there's a 2 E minus grad u. So I write that this whole thing is larger than, so we have grad u squared. This one I drop, it's positive. And this one I integrate by parts. And if you integrate by parts, you're going to get a boundary term. Has E minus grad u, but dotted with the normal, and that's 0. Okay, and then you get minus u divergence of E minus grad u, but that's also 0 by definition of E. Okay, so this finishes the proof. This one is larger than that one. Why do I call that L2 projection property? Because basically the property is that whenever you take a vector field and you project it onto gradients, right? A vector field is not necessarily a gradient, so you can L2 project it onto gradients. By definition of the projection, you reduce the L2 norm, right? L2 norm of the projection is. And so this is what is happening. This guy is, if you want an L2 projection onto gradients of that vector field. Okay, so let's see what this has to do with our problem. So let's imagine that I have a screen system, what I call a screen system, which is a box with a solution to minus Laplacian u equals this, and Neumann on the boundary. Let me now define E to be the gradient of u, but I extend it to Rd by just extending it by 0. Okay, so you take the thing that's grad u in the box and 0 outside. So it's extended to Rd. And now the question is, what is the divergence of that vector field? Okay, so there's two places. There's the inside, there's the outside. So inside, you get this. Outside, you get 0 because E is 0. But there could be a divergence on the boundary because E in principle is discontinuous. Right? So E is discontinuous. You have a vector field here. And then suddenly it's 0. So what is the divergence of such a thing? Okay, so this is something in the theory of distributions, if you want. When you have a vector field and there is a discontinuity at the boundary, the divergence of the vector field on the boundary can be a singular measure, but it's equal to the jump of the normal derivative. And this is something you see by Green's formula, Green's theorem again. Okay, so plus jump, so this is in the cube, plus jump of normal derivative. But here, precisely, the jump of the normal derivative is 0, because we've said that the vector field is tangent here. So this one is 0. So we have built it in such a way that it's tangent to the boundary, and as a result, there is no divergence created on the boundary. Okay, so this is very nice. Now, E solves the thing in all space. So now let's say that I want to consider the true electric potential generated by that configuration. Okay, so let's H be the true thing that's generated by this finite, this configuration in the finite box. So this configuration in the finite box generates a potential in all space, right? So this is in all space. You have charges here, but the field lives everywhere. The potential lives everywhere. Well, then H and E, they have the same. Okay, so then minus Laplacian H is equal to that. And that is equal to minus divergence of E. Okay, so the divergence of E is the same as the divergence of the gradient. Moreover, at infinity, they agree, because E is 0 at infinity, and H decays. Okay, so E minus grad H dot nu, I would say, equals 0 at infinity. So I can use the same projection lemma, the same computation as in the projection lemma, and find that the integral of grad H squared is less than this. And this is in RD, and this is in Q, because this thing lives only in Q. Okay, so bottom line, if you want to estimate the energy of a certain configuration, it suffices to have a sort of good candidate for an electric field. So E is called electric field. So it suffices to find a vector field, not necessarily a gradient, that has the correct divergence and whose energy you can estimate. It will give you a bound from above. Okay, so if you can find an E and you can get good estimates on that, then automatically you get estimates from above. And remember, things are going to be sandwiched, right? So eventually, what's going to happen is that this thing is not very far from being an equality. And this is why we call this a screen system, because you see, from the point of view of an observer that would sit here, so when you're here, this system generates a potential, but from the point of view of the energy, it's not very different. The energy is not very different from the energy that's in the cube. So in some sense, it's not very different from a situation where H is 0 outside. And so if you're sitting here, you can compute the energy almost as if this box was not generating anything. So let us see this in a slightly different variant. Right, so imagine I have two cubes now, Q1 and Q2. I'm going to show the subadditivity. So remember we have U, Q1 union Q2. We have UQ1 and we have UQ2. So in principle, these things are not the same. So let us build a competitor, which is a vector field that's grad U Q1 when we're in Q1, and grad U Q2 when you're in Q2. Okay, so we paste the two vector fields together. And what about these vector fields? Well, again, they are tangent to the boundary by construction. So there is no jump of normal derivative. And so there is no divergence. And when I compute the divergence, I find just the sum of the two divergences. So I find the sum of these Laplacians. And so that is equal to whatever is in that big box. And that is the same as minus Laplacian of the U of the big box. Okay, so I have two different functions, U1, U2. I take their gradients, I paste them. It's no longer a gradient, but I don't care. It's a vector field that has the correct divergence. And that is because things are tangent to the boundary, okay? So this is because no divergence on the interface. So thanks to that, this E is a competitor. And so I can apply the projection lemma okay, so by projection lemma, we find that the integral of grad UQ1, UQ2 is less than this test vector field, E squared. But what is that? This is just the sum of the two. Right? So we have shown that the F Q1, Q2 is less than F Q1 plus F Q2, and that's the subadditivity. So of course, what you have for two cubes, you can generalize. Right, so now if I have my whole big system and I want to estimate its energy from above, I can just cut into cubes. I can find like screened systems in the cubes, and I bound the energy from above by the sum of the energies over the cubes. And you see the benefit of this is now you can do some sorts of copy-paste of configurations. You can just paste them, and you can estimate the energy by the sum, which is in principle not clear at all, because in principle, you know, when you have two cubes here, they should interact. There's points here, points here. You should sum all the pair interactions. And by reducing to this electric field formulation, if you have screened cubes, then you can start to add, and they become almost independent if you want. But this is only true if you put screened configurations. So the idea is that we're going to show that in some asymptotic limit, this is not very far from the truth. So like the true configuration, when you look at it in a box, it's not exactly neutral. It's not. But it's not too far from it. And this sort of additivity picture is not too far from correct. OK, so now we have the sub-superadditivity. And now we can define associated free energies. OK, so it's going to be the k's. So the k of mu, so it's k beta, of course, in some region Q is going to be defined as the integral of E minus beta f Q. And the other one I'm going to call L. It depends on n also. And this one I call G, right? So maybe there's a normalization factor. I should take a look. So this is all in chapter 7. Yeah, so there's an n to the minus n. In the same way, this is just to normalize the fact that this thing is not a probability. OK, so once you've defined your two partition functions, so whenever things were subadditive, the partition function is doing the opposite. It's, of course, it's reversing all inequalities because you have the energy with a minus in front. OK, so log k is super additive, right? So I'm not writing all the entries, but it's kind of obvious. Because f is sub-additive, so this one is super additive, and the same for L. Now it's sub-additive. OK. So now let us consider the situation where mu is uniform. So remember, mu is the blown up of the reference measure. So it's going to vary slowly in any case because we're in a very big extended domain now. So this mu is expected to vary slowly. So in first approximation, I'm going to assume that it's constant locally. And if I'm going to assume it's constant, I might as well assume it's equal to 1. Its density is 1. Because you can rescale from 1 to any constant very easily. So let's first consider mu equals 1. Okay, so we solve all these things with right-hand side now. Sum delta xi minus 1. So in particular, the k quantities are defined only if the cube has a volume which is Rd, which is equal to the number of points in the cube. This is the neutrality condition. Neutrality condition becomes that number of points in the cube equals volume. Okay, so now what's nice with a constant density is that if you start to take boxes and you put them together, the density is always 1, right? You can start to put together. And so now the log of k 1 cube r, I can divide it by the volume. And by the super additivity, this thing is going to be increasing. All right, so it's like if I put two boxes together, take the free energy, divide by the volume, it has to be increasing. And the same thing, the other one. This one has to be decreasing. And my question is there a limit as r goes to infinity? Is there a sort of large box limit to these things? So you take a box, size r, you put a density 1, you put Rd points in there, and you try to understand if there's a limit to the free energy per unit volume. So the free energy per unit volume, that's also called the pressure in physics. The existence of a limit like that is called a thermodynamic limit. So the idea is, so you're going to have this, the first thing, log k over q bar, it's going to be increasing. Right? The other one's going to be decreasing. And the idea is, in fact, these two are not that different. They're not that different. So the question is, we're going to try to show that actually log k minus log r is not that big. And in particular, that it's much less than Rd. So if we can show that these two are actually not so different, then when you divide by Rd, it means they have the same limit. Right? They have the same limit. And we're going to call it f of beta. It depends on the dimension, so fd of beta. Right, so function depends still on beta and the dimension, and nothing else, because we've normalized everything to have density 1. Okay, so this height here is this fd of beta, and this is r, and this is log L over Rd, and this is log k over Rd. So if we can show this, and maybe even with a rate, it gives us a bound on the distance between the two, and it also gives us a rate of convergence to the limit. Okay? Okay, so why would we believe that these two are close? Well, because in the end, the only difference between the u and the v is the boundary condition. Right? You solve the same equation. You have a cube. You have one thing that solves with Dirichlet, one thing that solves with Neumann. But when the size of the cube is becoming very, very large, this sort of effect at infinity should sort of decay fast when you come inside. Or at least that's what you can hope. And so, sort of in the bulk, when you're well in the middle, these two should be the same, and that means that the energy should be the same up to surface effects. So we expect surface effects. And what is the size of the surface? Well, it's now r to the d minus 1. Right, so when you have a thing of volume RD, the surface is RD minus 1. So at best, the rate we can hope, the best rate we can hope would be 1 over r, because you divide by RD, so RD minus 1 divided by RD is 1 over r. And we cannot do better. This is really the limit. But we can hope to do that. And now if you think of it, there's a lot of problems in statistical mechanics where this is one of the main questions, right? You have something in a big domain, and you're trying to show that the effect of the boundary that's far away is kind of negligible. Right? You see it in Ising model analysis, for instance. So this is a standard problem, and we're going to have to face it here in this particular case. So we will get a rate that's almost 1 over r. There's going to be some corrections due to temperature, but and this is very similar to what's obtained in homogenization by this method on boxes. But at this level, we're kind of stuck there. But it's going to give us an expansion of the free energy with an error rate. So how do we prove that these things are close? The keyword, there's a keyword, that's the screening procedure. So this is, in some sense, where the heart of the technical work is hiding. It's in there. And I'm going to explain the procedure with a picture, not with equations. Just so you get the idea, because the idea is not that complicated. So the screening procedure, it was actually introduced in work by Sandier and myself on a different problem, on the problem of vortices in Ginzburg-Landau. I mentioned to you that there was this interest in problem with vortices in models of superconductivity and superfluidity. And that construction also, there's a similar construction appeared in work of Alberti, Choksi, and Otto on a related problem. Again, always the problem with being to go from a question with no boundary condition to a question with Neumann boundary conditions, and relaxing the gradients, the gradient constraint, to just being vector field constraint. Okay. So I'm going to draw a box when things dry. And the question is going to be this. We have a box, and we have a configuration in the box with points and a mu. And now I know nothing about what it's doing at the boundary, or maybe I know that the field is 0, the V is 0 at the boundary, but it doesn't matter. Just take any configuration in the box. The question is going to be to modify it in order to make it into a screened configuration. So we're going to take the potential and we're going to change it to solve the Neumann boundary condition. And the question is going to be doing this without changing things too much. So you want to not perturb the configuration too much. You want to not add too much energy to it. And you want to not add too much entropy either, or not lose too much entropy. So you don't want to lose too much volume of configurations when you do this replacement. Okay, so let me draw the box. Okay, so we're given some box, some solution to something like this. And we're going to not think of v, but just think of e, the integral of grad v. So we're going to sort of forget that it's a gradient. We're going to assume that this configuration has not too much energy in the box, so something reasonable, like maybe something like that. We could do with a little worse than that, but okay, this seems reasonable. Typical configurations will have energy less than the volume. So we're going to assume we know this. And remember, this configuration is arbitrary, so it's not necessarily neutral. So the first step is we're going to use a mean value theorem to find a good boundary and gamma, I want it such that the integral over gamma, so now it's a boundary integral, right? Is less than maybe CRD over L. So what is L? I'm going to give myself some sort of layer size. And my good boundary is going to be this. It's going to be at distance L from the boundary of the box, right? So this is size R. This is size L. So the idea is we're going to completely delete the configuration near the boundary. There's going to be this layer of size L. We're just going to delete it and replace it by a configuration that we make by hand. So if you try to apply the mean value theorem, it tells you, okay, if I integrate over contours, eventually I get bounded by this. So if I give myself a thickness that's very thin, my estimate will blow up, depending on the thickness, but I can get something of that order. Right? So, okay, so L, we want it to be much less than R. And this way, the configuration that's inside this orange thing is kept untouched. So here, we don't change. Here, no change. We keep the E, we keep the points, everything's the same. Now, outside, we delete. Okay? Delete everything. Just throw it to the garbage. And then what we're going to do is we're going to replace now outside by something done almost by hand. So we're going to find little cubes or rectangles or whatever of size L, and maybe I need several layers of them, I don't know. The size of the cubes will have to be somewhat quantified because we need integers. And on each of these cubes, like that, we're going to create another electric field, so another E. So this is this and that. Okay, so I'm zooming on one of these cubes. So here, my E inside is given. Inside, I have an E that's given. And what I want is I don't want to create any divergence on the boundaries. So I want to keep E dot nu. I want to have E dot nu to be the same. E dot nu here forces to me E dot nu here. So let me call phi E dot nu. So I'm going to call this. I guess I want that the E dot nu match on both sides. And here I just want to put E dot nu equals 0 on the yellow part. Okay, so I want to solve minus Laplace W equals something like this. And I want the Neumann condition to be this phi. That's equal to something given or 0 on the other part. Okay, so you have a rectangle, and now it's not 0 Neumann, but it's a prescribed Neumann. So the Neumann you have from the inside, and then 0 on the other parts. And then we're going to extend to 0, 0, 0, until we reach the boundary, and Neumann data will be 0. Okay, so can you do this? So here, there's going to be a compatibility condition again. So the fact that you have this phi that's given to you, you want to put points, you want to put mu. So basically, the volume of that cube will have to be something very specific so that you can put an integer here. But it's okay. You can modify a little bit your little cubes until the volume is this precise something quantized. You know. So once you've solved this, then you take E equals grad W in that little cube. And then you just glue together all these E's. So the E from the inside, the E on the small cubes, you glue them. You have not created any divergence. And the total divergence in the whole big cube has the correct form. Okay, so now you take E equals the E inside plus the sum of these new EI's on these little cube QI's. And the divergence of E has the correct form. And it's tangent to the boundary on the big cube. So the whole thing is now screened. So the compatibility conditions basically make it so that in these little yellow cubes, you're going to put in total exactly the right number of points so that the whole thing becomes neutral. Okay, so if you started from, maybe you started from a bit too many points, you're going to take whatever you have inside and maybe put way fewer points in this layer to compensate for the excess. If you had too few points inside, it's going to make you put more points near the boundary, and you're going to always compensate. What guarantees that you can compensate is this condition, which is called the screenability condition. So it's telling you that you're starting from something that is not too crazy. Right? If you start from a configuration that's absolutely crazy, it will be too difficult to screen it. If it's reasonable in that sense, the construction shows that you can actually screen. So the point is, how are you going to pick these points here, and how are you going to estimate the energy that's living in these yellow boxes? So the energy in the yellow boxes is going to be estimated by elliptic estimates, right? You're solving elliptic PDEs with Neumann boundary condition. There's sort of standard machinery of elliptic regularity is allowing you to bound in each little cube like this. You're going to bound in terms of the volume, but in particular in terms of this phi on the boundary plus other stuff. And the phi on the boundary, you bound thanks to this. So when you sum all the contributions over the cubes, you're going to control by that. Okay, so this is what is going to be interesting. And what's good here is you're going to get some factor which is relative to the size of the cube, and that's going to be relatively small compared to your problems. Okay, so the idea is that when you sum all these added energies on these cube on the layer, you're not going to get something too big. You're going to get something that's of the order of the volume of that layer. So you see, this is much less than RD, as long as L is small enough. So if you do that, you can construct a configuration, global configuration, that has the same energy as before, plus maybe a little error. Plus maybe a little error. Okay, so added energy is not too big. So less than what you had. So imagine what we had was the G, the cube, plus maybe something like that. So this is relatively small. And so there remains one question, which is, what points do I put here? Yeah, I know the boundary condition, I know the mu, but here there's still a lot of freedom, right? You know how many points you should put by compatibility. You don't have a choice of the number of points in each little cube, but where do you put them? So originally we were just putting them by hand, like we were putting them like on a lattice, saying, okay, we can put them on a lattice, maybe let them move a little bit. But you have to remember that this is meant to go inside a Gibbs measure. So we have to not only do things for one configuration, we have to do it for all configurations. We have a whole family of configurations. And so we want things to be sampled. And in fact, the way to pick the points is to sample them again according to a Coulomb gas in the subcube. So we have this sort of, we define these partition functions in cubes, right? So we can define the partition function in a cube with a slightly different boundary condition if we want. So we're going to just sample the points in the small cubes according to the Coulomb Gibbs measure in the cube, in the small cube. Okay, so I spare you the details of controlling. Basically that the entropy is not too messed up by that. So the energy is not too messed up. This is this. And the entropy is not changed by more than beta, so sorry, RD over L. So that's something that, takes some pages. It's in the notes. I don't recommend reading it, honestly, but yeah. So just message is you can do it. Everything can be done. There's a procedure. It's a construction, so it's always technical. And at the end of the day, you show this way that the F, right, of the configuration is less than the G. So this is F now, plus RD minus 1L. And you can prove also at the level of the free energies a similar thing. Okay, so conclusion, a log of k minus the log of L in the cube. Okay, let's do in the cube. We can show is less than C. You're going to get beta in front of the energy error, because energy always comes with a beta. And then you're going to get the entropy error. And I'm just mentioning these things because you can see now that if you optimize over L, it leads you to something interesting. It leads you to picking L equals 1 over square root of beta. That's the thing that makes the two errors the same. And it's telling you that if you want your thing to be, this error to be, as small as possible, you're going to be stuck at 1 over square root beta. And because L has to be less than R, right? L is here, and this is R. So R has to be bigger than 1 over square root beta, which is an interesting length scale. When beta gets small, this can become large, right? If beta is not small, then we don't have to worry, but this is only when beta is small. So when beta is small, there's a sort of threshold that you cannot go below. And basically, when R would be smaller than that, you cannot screen. It's like the screening is not giving you the same good bounds. Yeah.
If the two terms must be on the same side, maybe there is a d minus 1 in the entropy, or?
Yeah. Maybe it's a d minus 1. I think it's a d minus 1. Yeah. Thank you. I can check in 1 second, but okay, I don't have it like here, but I think it's done. All right, so at the end of the day, finally, what we can show is that log k 1 and qr divided by rd minus its limit, right, is going to be less than essentially C over R. So the rate of convergence that I was showing you on this picture, thanks to the fact that you have two quantities and the distance between the two is like 1 over R, you're also going to get rate of convergence 1 over R. And moreover, when you have things that are subadditive and things that are superadditive, and eventually they're almost the same, it means that each of them is almost additive. Right? So each of log k log L is almost additive. So thanks to the screening, what we have is that, right, if you have two cubes, Q1 and Q2 mu, you can now start to say that it's the same as the sum of the logs plus an error which is going to depend on Rd minus 1 and has some betas in there. Okay, so this is the almost additivity of the free energy. So now if my mu was uniform, I could just say, okay, if I have a domain like this, the free energy of the whole thing is just going to be like the volume up to some small errors. Because in each thing I get an FD of beta, and then I have the volume, so I can just add the volumes, right? And this would be the final answer. If the density is not uniform, we're going to have to see how things scale, and we're going to get an expression that's a bit more complicated, but it's going to involve this function FD of beta and also the density. Okay, so this is step one, or this is a result that's already interesting on its own because it's going to give us an expansion for the partition function to next order. But we're going to see that this afternoon. And what I want to show you now is that this whole discussion allows us to get what we call local laws. So what did we see 2 days ago? You may remember that we saw something like this. We control the exponential moments of the energy, and now I'm going to do it in blown up scale. Right. The exponential moments of the energy, we can write them as the log of the ratio of two partition functions, one that has temperature beta, one that has temperature beta over 2. And by using the bounds that we have on all of them, we had a bound like this. So this is macro scale control. So go back to 2 lectures ago. We had this macro scale control. I told you, oh, this is concentration around mu. It shows you that the empirical measure is close to mu. Okay, so now this tells us that if we're in a whole big region, which now in blown up scale has volume n, so this is the n 1 over d size, and this whole thing, the energy is typically like the number of points or like the volume. It's all the same. Volume, number of points, similar. And now question, or let's say theorem, this is what we can prove. So it's always the Coulomb case here, is that for any r that's bigger than a certain rho beta, which is called a minimal scale, we have the same estimate for the restriction FQR. But when in the right-hand side, I put, instead of n, I put the volume, RD. And what is rho beta? Rho beta is related to this threshold I told you, 1 over square root beta. Okay, so the way to read this theorem is, okay, in the whole box, I have typically an energy equal to the volume. And now I can take smaller boxes. And again, I have an energy that's like the volume. I can take even smaller boxes. So what is the minimal size of the box that we should take? Well, boxes of size 1 will contain only a few points. Right? So you cannot go below that scale. That's why R has to be bigger than 1. Below 1, you have maybe not even 1 point in your box. But anything that has a large number of points, any box that can contain a large number of points, has an energy which is actually not more than the size of the box. Okay, so you can do, you have a lot of scales between 1 and n to the 1 over d. You can do n to the epsilon for any epsilon between 0 and 1 over d. And in each of these mesoscales, they would be called mesoscale cubes, you have an energy which is not more than the volume of the box, measured in these exponential moments terms. Okay, so from there you can deduce things that you may want to know, like for instance, how many points are in that box? Well, you know that this F is going to control, it's going to be a good measure of the difference between the empirical measure and the mu, so it's going to tell you something about the number of points in the box. It's not very far from the volume of the box, or the integral of mu in the box. It's going to give you some bounds on the difference. There are not sharp bounds, but there are still already small errors. So this is a manifestation, if you want, of a certain rigidity of the system, right? You have the system, it's very big, but things localize really well. Like you cannot have a concentration in one place. Things have to be very well spread out, and they have to follow the background measure very well. So what is the key word for proving this theorem? Now we kind of have all the ingredients in our hands. But maybe I'll show you the computation this afternoon. The idea is to do a bootstrap on the scales. This is done by bootstrap. So first, from this relation, we know it's true at the big scale. Okay, so it's true for the biggest scale. R is n to the 1 over d. Remember, we're in blown up volume. And then you want to do a sort of induction, right? So assume you have it down to a certain scale R. You have it. And you have a certain, what's important here is you have a certain constant C, right? Like, so assume on a box of scale, say 2R, I'm going to say. So I do Q2R. And I assume it's less than C, beta, chi of beta, 2R to the D. And what you want to do is to show that it's true for R. Okay, so if it's true for 2R, it's true for R. And show same thing. But with the same constant, that's what's important. And I don't want the constant to deteriorate. Otherwise, I would have accomplished nothing. Okay, so this is going to be the task. Assume it's true at size 2R. Show it's true at size R. And what do we get from assuming that it's true at size 2R? Basically, we get to know that things are already quite good. And in particular, if I look at the box of size R, I have an energy bound from the box of size 2R that contains it. And that's going to give me the screenability that I need. You remember there was a screenability condition. The configurations don't have to not be too crazy so that you can screen them. So We're going to get screenability of almost all configurations, not all of them, but most. And then that's going to allow us to screen and to get the thing at size R until we saturate at the minimal scale. Minimal scale, we would lose the same constant that's here. Okay, so this afternoon I'll start by showing you the argument that allows to use the screening to deduce that. It's not very long. And then I will move on to getting free energy expansions for general density and the central limit theorem by what's called the transport method for the Coulomb gas, and especially in 2 dimensions. Questions here? Yeah.
Could it be simpler if we only assume the gas is a soft sphere or hard sphere?
Yes, possibly, but you see, this approach is very, very dependent on the fact that we have the Coulomb interaction, because we start from the Coulomb interaction and we have this electric reformulation in terms of this integral of grad h squared. Right? So I have these quantities that are local quantities, and now I can sort of sum them, copy-paste them. If you do hard spheres, then yes, maybe you can start to define the energy in the box and try to see if it's additive. So somehow you have to get rid of possible long-range interactions, which is true in hard spheres. But you would have to sort of find an analog framework to work with. It's not impossible, but it is different. And I'm not sure that in the particular case of hard spheres, this would be the most efficient. Because you have other techniques, right, that are around for many things. So it turns out that in this Coulomb case, there's not much else that works. So this is a good technique. But so I don't know. It's an interesting question to work out other interactions. What is sure is that when the interaction is very short range, so decays very fast at infinity. So for instance, if you take the hypersingular case S bigger than D, you can do things in the same way. The additivity becomes easy. So if interaction is very short range, again, the screening somehow comes for free. You know that 2 boxers are not going to interact very much because the interaction decays very fast. So you can sort of get the additivity for free. So I think it's more interesting to do it here because it doesn't come for free. It's a priori the Coulomb is pretty long range. So the fact that it still comes is a bit of a surprise in some sense. Yeah.
And the screen individual areas molecule are on the same scale, on the same size?
L, this little L,
okay.
Length scale, yes. And you put several layers because you just need to fill up to the boundary. You know, you delete the whole thing and then you can screen quickly, but then you need to fill up, right, to recover your cube. Well, thanks for your patience.